Hello everyone, it's my pleasure to share my research with you. I will talk about the enlargeable length structures, rigidity, and scalar curvatures. First, I will give the background about the scalar curvature, and then introduce the enlargeable length structure. Then take application to locally catered manifolds. And we will see the difference between the locally catered manifold and the non-positive curved manifold. And I will also define the positive NV scalar curvature and show the existence of positive NV scalar curvature. I will also show the rigidity by using harmonic method with condition C. First, let me record the definition of the scalar curvature. So, giving a smooth Riemannian manifold, the scalar curvature can be defined as this formula, and we can see that the scalar curvature can infect the volume of the small board. And in the two-dimensional, the scalar curvature is the Gauss curvature up to a constant. So as we know, the Gauss curvature is a smooth function on the surface, and the scalar curvature is also a smooth function on the smooth manifold. So we can see the scalar curvature may be a Gauss curvature in higher dimensions. And we know if the Gauss curvature is positive, then we have a Gauss-Bonnet theory, implies that the manifold must be the two-dimensional spheres. So that's the natural question is that which closed smooth manifolds admit a Riemannian metric with positive scalar curvature? Well, following I will just say is the PSC matrix. Now, why we just care about existence of PSC matrix and not care about the negative scalar curvature, since we know that the Kasten and Varna, they show if a smooth function and the dimensional is bigger than 2, and the function is negative in some point, then they must be admit a smooth Riemannian metric G such that the scalar curvature exactly is the function H. And in the special case, we can see H is just the -1. So we see that every manifold they admit a metric G such that the scalar curvature is the -1. Of course, the dimensional need to be bigger than 2, since the two-dimensional the negative Gauss curvature will be implied the surface must be the genus bigger than 1. And how about if we just require the scalar curvature is non-negative and somewhere is positive? Then we know you can use the each flow can show that they also admit a metric G0 such that the scalar curvature is positive everywhere. And for closed-oriented three manifolds, if they admit PSC matrix, then by the Thurston and Perelman's result, we know that the manifold must be spherical three manifolds, S2 cross S1, or the connected sum between each other. And in 4-dimensional, they will be relate the cyber-latent invariance. So there's a different stories as the topological in difference between the 4-dimensional and high-dimensional. So in high-dimensional, for the simply connect, then Gromov-Lawson, they showed that if the manifold is non-spin, then it carries PSC matrix. And later, Stolz, they showed that if the manifold is spin, then it carries PSC matrix. If and only if the alpha invariant vanish. So here, the simply connect is essential conditions. Our goal is to find the obstructions to the existence of a PSC matrix on a closed non-simply connect smooth manifold. Here is the well-known conjecture said that closed aspecial manifolds carry not PSC matrix. Gromov-Lawson, they introduced the enlargeable manifolds as an obstruction based on index theory. Later, they can relate the spin assumption, but required dimensional is less than 8. And Citrini, Schick, they used the Shenyang's result to show that a closed enlargeable manifold cannot carry any PSC matrix. Both enlargeability mentioned are defined on Riemann matrix and need at least C1 smooth for the mass. And we will define the enlargeable length-structure for length matrix space, and the mass only required to be continuous. Then we will given a new obstruction to the existence of PSC matrix and positive MV scalar curvature on a closed manifold. Now, let me record that the definition of the length matrix in a metric geometry. So if the metric space is a length metric space, then the distance between each pair of points equal to the infimum of the length of curve joining the points. And we know that a closed topological manifold admits length matrix. And matrix induced by smooth Riemann matrix on a closed smooth manifold are length matrix. And each two such length matrices are strongly equivalent. Moreover, length matrix can be induced by continuous Riemann matrix on a closed smooth manifold. However, unlike Riemann matrix on compact smooth manifolds, different length matrices may not be strongly equivalent to each other. For instance, the matrix induced by Finster matrix and the other one is induced by Riemann matrix, then they may not be strongly equivalent to each other in general. And the length matrix can be lifted to the covering space. They say that means that if pi is a covering map, then we can lift the metric or S to the H height. Well, more each length metric D or S lifts to a unit length metric D height for which the covering map is a local isometry. A topological manifold endowed with a complete length metric is called epsilon hypersurfic if it admits a continuous map F to Sn, which is constant and infinite of non-zero degree and such that the ellipse is constant smaller than epsilon. Here, the constant and infinite means that there is a compact subset such that F maps the complement of the compact subset to a point in Sn. And in this talk, our Sn is endowed with standard round matrix. And here, the epsilon hypersurface is defined by the Gromov and Lawson. They require the mat is the C1 smooth. So since they need to use the index series, and here our only required mat is the continuous. So now the definition given is the enlargeable length structure. So a length metric D on a closed orientable n-dimensional topological manifold is said to be enlargeable if for each epsilon, positive epsilon, there is a unit or there is an oriented covering manifold endowed with the induced metric D tilde that is epsilon hypersurface. An enlargeable length structure on Sn is a strongly equivalent class of an enlargeable matrix. That's why I mentioned that each length metric induced by the remaining metric are strongly equivalent to each other. And the enlargeable remaining length structure on a closed oriented smooth manifold is an enlargeable length structure that contains a length metric induced by a remaining metric on the manifold. Now, the example is that the n-dimensional torus, they automatically admit a remaining flat matrix, and the remaining flat matrix is the enlargeable length matrix. So we have the torus, n-dimensional torus admits enlargeable length structure. And we know that n-dimensional torus is a potent example in the study of the scalar curvature. And enlargeable length structure can also be defined on a closed non-oriented manifold just by leaving the metric onto the orientation cover. There's two properties of enlargeable matrix. So if S and Y are closed oriented manifold with length matrix, and suppose that there exists a ellipsis continuous map F for S to Y. Also, we require that map is non-zero degree. Then if the metric on Y is an enlargeable matrix, then the metric on D is also enlargeable. And the second property is that the product of two enlargeable matrices is an enlargeable matrix. So we have the corollary that if a closed manifold carries an enlargeable length structure, then the manifold closed S1 also carries an enlargeable length structure. And we think this corollary is interesting because there's a conjecture which said that if a closed smooth manifold S admits a PSC matrix if and only if the S closed S1 also admits PSC matrix. So we are saying that this enlargeable length structure can be an obstruction to the existence of PSC matrix on the manifold called S1. And the other corollary is that if S is a closed smooth manifold and the matrix DS is induced by a Riemann matrix, and Y is another manifold. But we require that matrix dy is in the enlargeable length structure. And also we suppose that exists a Lipschitz continuous map of non-zero degree. Then S also carries an enlargeable Riemann length structure. So we have the theory that if S be a closed-oriented smooth manifold, then S carries not PSC matrix in its enlargeable length structures. Here we have the dimensional restriction because our proof of the theory is based on the Gromov spherical Lipschitz band, and Gromov spherical Lipschitz band theory is also based on the minimal surface theory. So there's a dimensional restrictions. But if the Shenyang's recent result is true, then we don't necessarily require the dimension smaller than 9. And Gromov's theory said that if the scalar curvature is bounded below by n times n minus 1, then all continuous map for S to the Sn, which is constant at infinity. And of course, we also require the map of non-zero degree. Then Gromov can show that Lipschitz have a uniformly bound. Lipschitz constant have a uniformly bound. And Gromov, he want to improve the constancy. So, and the goal will be that Lipschitz constant is bounded below by 1. But up to now is still far away. We can only show that at least the C is not less than 1/3, and we don't know. We cannot prove that the C will be bigger up to now.